Hey guys, in preparation for tomorrow's test, I'll be reviewing key terms, vocabulary, and how to do the calculations today on this video. So let's start out with the key terms and concepts. So these are all the things that you'll be responsible for knowing. Let me bring my computer a little closer. Okay, so you have to know, you have to be able to identify a transverse wave when you see it. You'll have to be able to identify a longitudinal wave when you see it. You need to know what wavelength is, what period is, where a crest is, where a trough is. You need to know what amplitude is and what frequency is. So in this video, I'll talk about all of these things, and in the next video, I'll go over the calculations for wave speed, frequency, etc. Okay, so let's get into this. So transverse wave. A transverse wave goes up and down. If you imagine, if you've ever been to a sports game and you've seen people do the wave and how the wave travels all the way around the stadium, well, that's an example of a transverse wave where the people just go up and down. Now the people, they don't move with the wave. They don't move with the energy of the wave. They just go up and down. And in fact, every wave is like that. So every wave carries energy but does not carry matter. So the perfect example of that is a wave of people in the stadium when they all get up and do the wave, and then the person next to him does the wave, and it just transmits throughout the stadium. Those people don't move with the wave, they just go up and down with it. So matter can go up and down or back and forth with the wave, but it won't travel with the wave. So anyways, let's get into transverse wave. So a transverse wave, the motion of the particles is perpendicular to the motion of the wave. So let's say the wave starts here. All right, so it creates this wave, and then you have the next wave, and the next wave. All right, these waves are moving this way, okay? And these up and down lines represent the particles of the wave. So these individual particles, if I put dots here, it represents the particles. Now these particles just move up and down. They move up and down with the wave, but they don't travel with the wave, okay? And this is an example of a transverse wave. With transverse waves, the particles move perpendicular to the motion of the wave, all right? So remember, perpendicular looks like this. All right, the particles go up and down while the motion of the wave goes this way. All right, so the particles move perpendicularly to the motion of the wave. And this is what a transverse wave looks like. It's also called a sine wave. All right, so up and down, that's a transverse wave. And it's just like taking a rope and tying it to a doorknob, and you swing the rope up and down, and it makes those humps. All right, and those humps, the waves travel to the doorknob. That's an example of a transverse wave. Okay, so then we have longitudinal waves. So we just talked about transverse waves, and that's the example of a transverse wave. Now let's talk about longitudinal waves. Okay, that's the transverse wave. Now we'll talk about longitudinal waves. So with longitudinal waves, the particles move parallel to the motion of the wave. All right, and you can think of it, imagine if you were able to place a spring on a doorknob, and if you were able to push on that spring, and then the wave traveled along the spring horizontally. Okay, so it would look like this. So here's the spring, and we have sort of a stretched out portion here, and then the spring gets compressed right here, and then we have a stretched out portion here, and then it gets compressed again. All right, so the wave is moving this way. Let's say your hand is here, you're pushing on, and the wave is moving this way. All right, the particles of the wave, each of these particles is moving back and forth parallel to the motion of the wave. Now notice how I said back and forth. These particles are just moving back and forth. Imagine a spring. This little metal portion of the spring is not going to suddenly end up over here when you cause a wave to run through it. It's just going to move back and forth in one spot, okay? Because waves carry energy, not matter. So the matter won't travel with the wave, it'll just go back and forth. All right? So what I mean by parallel, think side by side. All right? So down here, this is the motion of the wave, and then the particles go back and forth, back and forth. All right? They just go and they move parallel to the wave. So longitudinal, think parallel. Transverse, think perpendicular. Now for wavelength. The wavelength is the distance between two identical portions of a wave. Okay, I'll say it again. A wavelength is the distance between two identical portions of a wave. It can be the distance between the crests, the two crests of a transverse wave. That could be the wavelength. Or it could be the distance between the two troughs, the two bottoms of the wave. That could be a wavelength too. The key definition is that it's simply the distance between two identical portions of a wave. All right, that's sort of the easy way of thinking about it. It could be the distance between, on a transverse wave, it could be the distance between two crests of a wave, or it can be the distance between the two troughs of a wave. Okay? So there's the wavelength on a transverse wave. The wavelength on a longitudinal wave is a little different. It can be, the wavelength on a longitudinal wave can be the distance between the two compressions. Those are the two identical parts of a longitudinal wave. So this could be the wavelength. Or this could be the wavelength, the expansions. So it can be the distance between the two compressions, or it can be the distance between the two expansions, which are also called rarefactions. You won't have to know that word for the test. Just know that there are expansions and contractions to a longitudinal wave, and that the wavelength is either the distance from one compression to the other compression, or the distance between one expansion to the other expansion. Okay, that's the wavelength. Okay. Now I might have made it a little confusing up here. I noticed that I wrote troughs here. What I meant to write is wavelengths. The wavelengths travel from trough to trough, but this is a wavelength here. Okay? So now we know what wavelengths are. Wavelengths are just the distance. Wavelengths are a measure of distance between two identical portions of a wave. For a transverse wave, it could be the distance between two crests, or the distance between two troughs. For a longitudinal wave, it can be the distance between two expanded portions, or the distance between two compressed portions. It's distance. Okay? Now, a period is very similar to a wavelength, except a period doesn't measure distance, it measures time. It measures the amount of time that it takes for a wave to travel an entire wavelength. All right? So look at the similarities here. We have wavelength and we have period. See how they're in the same, they're going on this transverse wave, they're going from crest to crest. Okay? So a period is the amount of time that it takes for, in this example, for the crest of a wave to travel one wavelength. Okay? It's the amount of time that it takes a crest of a wave or a trough of a wave to travel one wavelength. Okay? For a longitudinal wave, it can be the amount of time that it takes a compression to travel one wavelength, or an expansion to travel one wavelength. All right? So just think about this. Just think that it's the amount of time that it takes a portion of a wave to travel one wavelength. That's probably the easier way to think about it. A period is the amount of time that it takes a portion of a wave, a certain part of a wave, to travel an entire wavelength. All right? It could be the crest of a wave, it could be the trough of a wave, but the key thing is to remember that it's the amount of time. So period is time, it's represented by the letter T. Wavelength is distance, and it's represented by lambda. Not so obvious there. You can tell why period's represented by a T because it represents time. But then, wavelength is represented by the Greek letter lambda. So wavelength is distance, period is time. Okay. So I've talked about this a couple times in this video already, but you have to be able to identify where the crest and the trough of a wave are. Well, the crest, and this only applies to transverse waves. These two terms only apply to transverse waves. So the crest is the very peak of the wave. It's the very peak. So here's a crest, here's a crest, here's a crest. When you hear crest, think peak. It's the peak of a wave, while a trough is the very bottom of a wave. Okay? So we talked about crest, we talked about trough. Now we're going to talk about amplitude. So amplitude is the furthest distance from resting place. So let's act like I'm going to do a dotted line here. And this is where the location of the wave would be if it were completely flat. All right? If the wave were flat, it would just be along this dotted line here. All right, but when the wave starts going, it develops a certain amplitude on it. So an amplitude is just the maximum distance from resting point to the highest or lowest part of the wave. All right, so in this transverse wave, this peak right here is the highest part of the wave. It's the furthest from the resting point. Okay, so that is the amplitude. I'm going to write amp, A-M-P. That's the amplitude. The amplitude can also be described as the distance between the resting point and the lowest point of the wave here. All right, so it's just whatever, really what it is, it's whatever point of the wave is furthest from the resting point. So the furthest point in this situation is the crest. The furthest point in this situation is the trough at this point right here. So that's the amplitude, amp. Okay? So amplitude is the furthest point from resting point. Okay, and I think what I'll do is I'll include all these definitions on your next worksheet so that you can actually see it too instead of just listening. Okay, now for the very last thing, frequency. Frequency is just the number of waves produced in a given amount of time. Okay, so let's say over 5 seconds we had 1, 2, 3, 4 waves produced, and then we have another situation where in 5 seconds we had 1, 2, 3, 4, 5, 6 waves produced. Okay? So it's the same amount of time, but the difference is one wave has higher frequency than the other wave, which causes it to produce more waves overall. So this wave has higher frequency, okay? Because it produces more waves in a given amount of time. So it produced 6 waves in that given amount of time, while this one only produced 1, 2, 3, 4. Okay, so this is high frequency, this is low frequency. Okay, and as you can see here, the longer the wavelength slash, also you could say the longer the period, that means the lower the frequency. So you said wavelength here, wavelength. Then you can also describe this area as a period, the amount of time that it takes the crest to travel, one wavelength. So the longer the period or the longer the wavelength, the lower the frequency. The shorter the period or the shorter the wavelength, the higher the frequency. So those are key things that you'll have to remember. Again, I'll include these definitions on your worksheet today so that you can study and get more practice with this. But go ahead and view the next video on calculations, and then after that I want you to start your worksheet.